Hi. Today, well, the title tells you what we're going to talk about, so let's keep going. A little bit different than usual. We're going to play a video of myself. This is a recording I made. If you've already seen this, I'm sorry. Hopefully we can skip to the end, but it might be beneficial to revisit. So I have two cans. We're going to go through slides 2, 3, 4, and 5 today. We're going to start with that. Slide 2 and slide 4 are recording things that you observed with these two cans. This is the dry one. So, I don't know if you can see. There you go. We got a burner. Starter likes to keep going. I'm going to put the burner on low. I don't know if anyone's going on with me because I just didn't spawn right now. If so, first can's going on dry as is empty. I don't know how well you can see, but there you go. Can. No contents. So the idea is we're just going to heat it up for a while. Don't know how hot it's going to get, how quickly, but we're going to watch. If you see anything coming up the top, there's a plastic lining inside these soda cans, so that's burning. So for the purpose of this demonstration, we're going to say time 1, or initial case, is right before I turn it and put it into the ice, and time 2 is after anything else happens. So right now we're before time 1. I think we're about ready. This one heats up in about 30 seconds to a minute. So I'm just going to take this. Water's cold. You grab it at the bottom and you turn it upside down into the cold water. So that's probably information for you. Let's see what happens. No. Dropped it. See? Let's give it another 10-15 seconds to heat back up to where it was. I still see some smoke coming out the top. I don't know how well you can see it. So take 2 on this one. So again, now we're transitioning into time 2. Seems like a lot of water was in there. For a second can here, our burner's still on. For a second can here, we're going to add back a tiny amount of water. This is a seltzer. Yeah. Let's say you're filled up to about here. So not a lot of water, because the idea is we don't want liquid water. We want oily water. So I'm going to let that heat for a while. This time if you see stuff coming out the top, it's good. Probably good to mention if you're doing this at home, it is fire. So like the airtight bag, don't get directly over the flame. Roll up your sleeves and there you don't want to catch anything on fire. Basically all the precautions you would take if you were cooking. But you can hear it. One of the things I can help you do, you can't always see the steam coming out, but it's really easy to see the steam if you trap it with something. So any glass, doesn't have to be a wine glass, but you put it on top. You see it fog up right away, so there's a ton of water vapor in there. But there you go, you can kind of see the steam coming up. I can see it on my screen at least. So that's a good sign that we're ready to go. So again, I'm going to try and be better about this, but we're grabbing at the bottom, we're flipping it upside down into the ice water, so make any observations as I do this. I think it's done what it's supposed to. Seems like it picked up a good amount of water. So credit to my son there for the first can being inverted. I heard him on the video. It is awkward listening to yourself, I'll say that. But I've drawn out what happened here. If you want to get that copied over, that's probably good for you to have. In both cases, water drawn up. In one case, the can imploded. The second case, it did not.
So to best investigate this, I want to, instead of go with our observations and then draw the theory, we have our theory. We've developed kinetic molecular theory. Let's use it. Everything else we've seen up until now has been consistent with kinetic molecular theory. This must be too. So we've got two containers. Just like, let's talk hypothetically. We use two soda cans. They have a volume of 335 milliliters, but you know what? Let's just use a nice round number. Two containers of equal volume. I did not draw them equal, but we're close enough. The first one contains 2 atoms of helium, and the second one contains 1 atom of neon and 1 of argon. Yes, argon and neon are slightly larger than helium, but remember, they're negligibly voluminous compared to the container itself. Because these are the same container, at the same temperature, at the same volume, with the same number of particles, we fixed everything, the pressures have to be the same. They're equal. That said, that gas pressure comes from collision. And it doesn't matter which particle makes a collision with the container, but as long as there is motion, random motion that makes a collision with the container, pressure will be exerted. All things considered, if the motion is random and constant, the chances that any one of these 4 particles will hit one of the walls over time becomes equal. So it would be fair to say that in both container A and container B, each of the 2 particles would contribute over time half of the total pressure of the container. I mean, that should, hypothetically, hopefully that makes sense. The idea being, it doesn't really matter which particle, it's just the number of particles that matters the most. So in this case, obviously 100% of the pressure would be due to the helium, but down here you could make the case that over time 50% of the pressure was due to the neon collisions, and 50% of the total pressure would be due to the argon collisions, depending on which one does the colliding. This hypothetically means we can pull back and now, like I said, instead of taking the observations and making the law and then coming up with a theory, we've done this whole process before. We have our ideal gas law. And like with the combined gas law and pulling out Boyle's, Charles, and Gay-Lussac's law, we could also pull out a law here. In the 2 cans, our volumes and our temperatures, I know that we were heating the cans, but the fact that we went from hot to cold is a constant within there. So really our two variables are pressure and number of particles. Because in one can we had air particles only, and then the other can we had water particles present in that can that went from being steam to being water. As the particles go from being steam to being water, they don't exert gas pressure anymore. So the number of particles decreased dramatically in the second can. That change in pressure lets you see the difference in impact of the air pressure, where in the first can the air pressure just forced water into the can. In the second one, it collapsed the can because the pressure inside went that much lower. But we're going a little bit past that to really understand this law, P over N equals P over N. If you do consider, a mixture of steam and air at a certain pressure, you can split up that pressure into those 2 components, air and steam. Just like we saw in the previous example with 2 particles of helium versus 1 of argon and 1 of neon, it doesn't matter which particles you're dealing with. A gas particle is a gas particle is a gas particle. That's kinetic molecular theory. Which means that you could say, looking at these, we're just going to subdivide our gas particles, and it just turns out that the way we split them is that the air ones are considered separately from the steam ones. And like the case before, the number of particles over time will be indicative of where the pressure comes from. You see a collision at this wall in both cases. Oh, there's that one. With the air and the steam. And the idea is that over time with the 80-20 mixture, that 80% of the pressure would be caused by steam in this example, and 20% would be caused by the air. Because it doesn't matter which gas it is. a mixture of gases will exert the same pressure as a pure gas as long as the number of particles are the same. And if the number of particles are not the same, then the pressure goes down. All of this adds up to a very, very interesting law. In a mixture of gases, each one will contribute what we're going to call a partial pressure. It's a fraction of the total pressure. So in the case here, you'll see that there is a pressure listed on both the air and the steam, 0.8 and 0.2. And so both of those are less than the total pressure, 1 megapascal. And in the case over here, we said that the two pressures are equal. But if we said how much pressure is being contributed by just the argon, that would be what we call a partial pressure. When you have a mixture of gases, you can subdivide, you can pull them apart. It doesn't matter which gas it is, but if they are different gases, you can mentally pull them apart and say, well, how much towards the total is this gas contributing? How much is this one contributing? And this yields this formula on the bottom here for partial pressures. The total pressure is just the sum of all of those parts, the 80% and the 20%, the 0.8 and the 0.2. In terms of comparing two gases, or the gases within, you can definitely come up with the law that says as long as the container is the same and the temperature is the same, the total partial pressure is proportional to the total number of moles, and the fraction of the total number of moles represented by each of the gases. So the fact of the matter is we can't necessarily always measure the number of particles in your container super easily. But if we had some way of measuring the partial pressures, the fraction, is equal to the same fraction of the particles. That is to say, I know on a mole basis that there are 4 times as many steam particles as there are air particles. If you want, we could try and pause this and you can count them up, but I don't need to count them up because that's what this law tells me. It's twofold. The first part being that you can just sum up the pressures, but the second being that you can use those fractional pressures to also determine a composition of your mixture, also known as a mole fraction. That would be N1 over NT. It's also represented by the Greek letter Xi, I believe, but it's either X or Xi. I don't remember which. It might be beneficial to look at 1 or 2 examples of this to really understand the point I'm trying to make, because I think this is one of those laws that you can explain, but it's the execution that really illuminates everything. You might need your reference table. I don't know if we do. But just let's take a look at these problems. If you want to do them on your own, this is a good time to pause and try and read and figure out. But I see that I've got 3 components to my mixture. All right, we've got N2 in here and CO2 and O2, and I'm not going to show them proportionally because that would take a little long, but I know my total pressure in here is 150 kilopascals. If we were to separate this into our components, just the nitrogen and just the carbon dioxide and just the oxygen, each of these hypothetical containers on their own would have a lower pressure than the mixture because there are fewer particles. That's how partial pressures work. It's almost like saying, imagine all the other gases were gone and I'm only focusing on just that part of the mixture. The nitrogen is responsible for 100 kilopascals on its own. The carbon dioxide is responsible for 24. Well, the total pressure is 150, so it just adds up. I can then therefore assume, just through subtraction, that 26 kilopascals is due to the presence of oxygen in the mixture. This is the power of Dalton's partial pressure law. You're allowed to, in a mixture of gases, mentally ignore the other components of the mixture if you only want to focus on that one part. And you can use that information to figure out, if you have most of the information, you can figure out that last piece. So here's another situation. I always like drawing pictures with these. It does seem like we have one container. It tells you the total pressure, right? This is the pressure of the whole mixture. But we want the partial pressures of the other 2 parts. That would be represented by pH2 and PO2. So just as before, it all adds up to that total pressure. But since we don't have any partial pressures, but we do have some mole information, again, we're going to relate those mole fractions back to the total amount there. So we've got 6.67 and 3.3 moles. So that's together roughly 10 moles of matter. If you want to do the math out, you can, but it looks to me like it's a 2-to-1 mixture, so a 2/3 and a 1/3 ratio. That's representative of the total 3/4 of an atmosphere. So if you do some quick arithmetic, this should be equal to 2/3 of the 0.75, which would give you 0.5 atmospheres, and then the rest would be responsible from the oxygen, so 0.25 atmospheres of partial pressure due to the oxygen. So like I said, it's one of these things where it's like you're worried about moles and you're worried about pressure, but it's really just mostly arithmetic and fractions. One final example, though, of this, which would be really, I'd be remiss if I didn't point out. The biggest application of this gas law is when you collect gas in a lab. It's really hard to collect gas in a lab because we're in a gas. So if you're doing a reaction that creates, say, carbon dioxide or oxygen or hydrogen, you can't see it. You can't measure it because you don't know where it is. And even if you did know where it is, it's not isolated from the air. As soon as it's created, it mixes with the air. So a lot of times, well, not a lot of times, every time. So the best way to measure your gas would be to somehow collect it separate from air. The simplest way to do this in a lab is to take a container, fill it with water, and then turn it upside down in another basin of water like I did with the soda cans, just without the heating, and by filling it with water. This way, when you turn it upside down, the water doesn't drain out. So you've got an upside down container full of water, and then you can put a little hose at the bottom. And then as the gas is created, the gas will bubble up and it will push the water out slowly. As there's more gas there, there's more pressure inside. The water level changes until the two pressures are equal again. Right? So this is still Dalton's law at play. When you're done, we have what you call a wet gas, because this gas isn't purely what you created from the chemical reaction. Collecting it over water allows water to evaporate into that container as well. So really, your product is, in the practice problem on the bottom, it's pressure of nitrogen plus the pressure of water vapor. And the water vapor pressure is equal to, well, the vapor pressure. So in these cases, if you had a table H handy, you could go to it. You can use water. I swear I'm going to read the right line this time, unlike that other video. And you can pull that vapor pressure. That said, usually the vapor pressure of water at most lab conditions is pretty low, but it is non-zero, and accounting for it will make your data that much better. In this case, we're talking about 40 degrees, so that's right here. It looks like the vapor pressure of water, I'm going to guess it's about 8 kilopascals. So we know that the total room pressure is 99.42 kilopascals. We don't know the pressure of the nitrogen, and we know that the vapor pressure of water is 8. All this yields about 91, 92 kilopascals for the partial pressure of the nitrogen. If you were going to then do some calculations, say you wanted to figure out the number of moles because you're doing a chemistry experiment, you're creating gas, you want to do some stoichiometry, that would be how you do this. You always have to include that if water is part of your procedure. Thanks for watching.